Hey everyone, so this is part 2 of aromatic substitution reactions. We're going to talk about activating and deactivating groups. We're going to talk about what all that means in the context of aromatic substitution reactions. So, what is an activating group? Right now, we've only dealt with reactions. Let me go to my laser pointer here. We've only dealt with reactions with benzene, right? So you saw in the previous video that we were only doing electrophilic aromatic substitution on benzene or very similar benzene derivatives, right? And with benzene, there's no substituents, right? It's just a six-membered ring and it's conjugated. There's really nothing special about it. But now we need to expand our discussion to include reactions of aromatic compounds that already possess substituents. Okay, so they have substituents. For example, if I have a benzene ring with a methyl group on it, right? The methyl group is a substituent. And hopefully by now you know that that's called toluene, right? That's a common name for a benzene with a methyl group on it. But if I'm trying to do a nitration on this, right, because you guys know that if I have benzene, I can do a nitration on this and just get a nitro group, right, with HNO3 and H2SO4. We saw that in the last video. But what happens now when I have a methyl group, right? Does this methyl group have any sort of effect on the nitration process? And the answer to that is that there are two issues that arise when you're trying to add a group, like a nitro group, to a ring that already has one or more substituents. So the first thing is that the methyl group affects the rate of the nitration, how fast it happens, okay? And why is it that this methyl group has an effect on how fast this nitration is happening? The reason for the effect on the rate is the methyl group is set to activate the ring. Okay, what do we mean by activate the ring? So you guys remember that methyl groups or any sort of alkyl group, like a methyl group, is electron donating, right? You guys know that if you have a tertiary carbocation, for example, right, the tertiary carbocation is more stable than a secondary carbocation because a tertiary carbocation has alkyl groups that are adjacent to the carbocation that are donating electron density to the carbocation to stabilize it, right? So the surrounding alkyl groups on a tertiary carbocation are donating electron density to stabilize the carbocation, right, from those surrounding alkyl groups. Kind of the same idea here, right? I just described hyperconjugation, basically. The methyl group is donating electron density to the ring through hyperconjugation. And if it's donating electron density to the ring, what that means is if the ring is trying to behave as a nucleophile towards electrophilic aromatic substitutions, if it's trying to be a nucleophile, it's pretty good that something's donating electrons to the ring, because if you have more electrons going in the ring, then you have a better nucleophile, right? You guys know that negatively charged or partially negative anything really, any sort of atoms that have that quality or molecules that have that quality of having more electron density, they're going to behave as better nucleophiles, right? And this will give a faster reaction. So that's the first effect of a methyl group, is that it activates the ring by having some electron density donated to the ring. The second effect, and this is arguably the more important effect here, is where does the nitro group go on the ring, right? Meaning, what is the regioselectivity of this reaction when you have a methyl group and you're trying to do a nitration on a benzene ring with a methyl group? What do I mean by regioselectivity? You guys know regioselectivity means what region are we going to have this reaction happen? Is it going to happen at this part of the ring or this part of the ring, right? There's all these different positions or regions where the nitro group can go. Now, is it selective for one region, another region, right? And how do we know that? So there are three possible places that the nitro group can go. They can go on what are called the ortho, meta, and para positions. And if you don't remember what that is, we talked about that before. Let me just go back to my pen here. What is an ortho, meta, and para position? Well, if I look at this ring, the groups that are right over here, okay, that's relative to the methyl group, relative to the substituent. These are called the ortho positions. I want to label them O for ortho. Okay? Remember, this is relative to where the substituent is. Right? So these are classified as the ortho positions. The meta positions are right over here. These are meta positions. Okay? And then the para position is right over here. P for para. So you got ortho, meta, and para. Notice that there are two ortho positions, there's two meta positions, but there's only one para position, okay, on a ring. And the question is this nitro group going to end up on the ortho, meta, or para positions? It turns out that when you run this reaction, right, imagine I run this reaction in a lab, what's the distribution of products that I can get? Because I can get a nitro group on the ortho position, that's called ortho nitrotoluene, at the meta position, and at the para position. If you look at the product distribution, right, notice that the product distribution is just from 0 to 100%, okay? Notice that you're getting a lot more of the ortho product, you get a good amount of the para, and very little meta. So the nitro group is the minor product here, and the ortho and para products are the major products here, okay? And you're probably wondering why. Why is it that the nitro group is ending up at the ortho and para positions and the meta position is minor? What's going on over there? Because now that we know that the ortho and para positions are the major products, the methyl group is said to be an ortho-para director, meaning it's directing substitution exclusively at the ortho and para positions. Okay? So why is this happening? Why are we getting more ortho and more para? Well, the only way to answer that question is to look at the sigma complex. You guys remember what the sigma complex is? It's the carbocation that you get after you've reacted your aromatic ring with your really, really good electrophile. You guys remember from the last video that you need a really good electrophile for a benzene ring to react. Or in this case, it's toluene, but really an aromatic system to react with anything, right? If an aromatic system is going to react with anything, it's got to react with a really good electrophile. And we saw in the last video that NO2 positive, or a nitronium ion, is a really, really good electrophile. Why? Because that nitrogen's positively charged. It's dying to get some electrons right now, right? Nitrogen is super electronegative. It wants electrons. So let's just see what happens when we now take a double bond from the aromatic system, break aromaticity, have it behave as a nucleophile, and attack that nitrogen at the ortho position, right? Which is right next to the methyl group. So with an ortho attack, you end up with having a nitro group at the ortho position, and now you have a positive charge that's adjacent or right next to the methyl group, right? And you guys can see that we can draw resonance structures for this sigma complex, right? And right now what we're trying to think about is this sigma complex stable? Is it happy to be the way that it is, given where we had the nitro group end up? Because we have the nitro group end up at the ortho position, which causes the positive charge to be right over here. And you'll notice what I have said over here is the sigma complex obtained from the ortho attack has a positive charge delocalized adjacent to the electron donating CH3 group, which is highlighted in green. Right? Now, this is giving a more stable sigma complex. why is it that this is a more stable sigma complex? Why is it that it's a good thing to have a positive charge next to an electron donating group? Well, you guys know this, that any sort of positive charge that is surrounded by groups that can donate electrons towards it is going to be a lot better of a situation, right? Kind of like how we describe a tertiary carbocation, right? Why are tertiary carbocations stable? They're stable because the surrounding donating alkyl groups are feeding electrons towards the positive charge, right? So notice that this positive is right adjacent to that CH3. Really good situation there, right? Because now you can have electrons donate and satisfy this positive hole that you have. Realize that's not always the case, right? Like you draw the other resonance structures, it's not like the positive is stabilized in this one or in this one. It's best stabilized in this one. But the fact that we have that opportunity to stabilize this positive charge from the ortho attack makes it so much better to have that attack happen ortho. Now, if you don't believe me, let's look at what happens when we have meta. So if you have a meta attack, let's just look at the sigma complex when the nitro group ends up at the meta position. If you have the nitro group end up at the meta position relative to your methyl group, you can see that the positive charge is delocalized throughout these resonance structures pretty nicely, right? But none of these resonance structures have the positive charge adjacent to the CH3, right? It's not stabilized by the donating methyl group, right? The electron donating effect of the methyl group. Nowhere does this positive charge end up anywhere near the methyl group like the ortho attack did, right? The one that's highlighted in green. You don't have that situation here. So the sigma complex obtained from the meta attack isn't stabilized, right? Because it doesn't have a positive charge delocalized adjacent to the CH3. Now, what about the para attack? If you guys look at what happens when the nitro group ends up on the para position, the positive charge, if you delocalize this sigma complex positive charge, you'll notice that the positive charge eventually does end up adjacent to the CH3. Hey, that's great. Because now we have that positive stabilized through the electron donating character of the CH3, right? And notice that this is only happening with the ortho and para attack and not at the meta position. So this comes to show that the reason why a CH3 group on a benzene ring is ortho-para directing, meaning it's going to direct the nitro at exclusively the ortho and para positions, it's because of the stability of the sigma complex, right? That we just saw. So that is the influence that this has, and there's other groups that can activate the ring. So we just saw how a methyl group is really good at activating a ring, donating electrons to the ring, right? Stabilizing the sigma complex. There are other activating groups. So we saw a methyl group. What about a methoxy group? What's a methoxy group? A methoxy group is an OCH3 group, right? Meth for methyl, oxy for oxygen, methoxy group. This is basically an OCH3 on a ring, right? Now check this out. A methoxy group in what's called anisole, that's the technical name for this molecule, is anisole. Like toluene is when you have a CH3 on a benzene, right? Anisole is when you have an OCH3, a methoxy on a benzene, okay? But bottom line is that the methoxy group in anisole activates the ring 400 times more than toluene, right? So this is a way better activating group than a methyl group, right? Methoxy is way better than methyl. Why is a methoxy group a better activator than the methyl group? It's because a methoxy group, even though an oxygen withdraws electron density from the ring through induction, right? Because oxygen's electronegative. It's going to withdraw electron density. It can also donate electron density through resonance. And how does an oxygen donate electron density to the ring? Well, you guys can see that there's a lone pair on this oxygen that can, through resonance, donate electrons into the ring, right? This is a valid resonance form of this. And you guys can see that there's a negative charge in the ring. So this oxygen is really feeding electrons to this, this ring. And it can keep donating electron density through other parts of the ring, right? You guys can see how this lone pair can be delocalized even further. And notice that the negative charge in the lone pair ends up exclusively at the ortho positions and the para position, right? Notice that the negative charge is not touching the meta positions at all, okay? Just really take note of that, because now you can see an added effect, right? Now that you have that negative charge delocalized on the ortho and para positions, it's activating those ortho and para positions for a nucleophilic attack, okay? That's yet another reason why we see that the ortho and para positions are substituted, okay? Now, this just basically tells you that all activating groups, they're also called activators, are ortho-para directors. That is a general rule of thumb, okay? And remember, the key thing between a methyl group and a methoxy group is that there's a lone pair that's adjacent to or right next to the aromatic ring so that it could donate electron density. If there was no lone pairs here, it wouldn't be able to do that so well. But because of that lone pair, it's able to donate electron density to the ring that much more, right? A CH3 doesn't have a lone pair, right? It just donates through hyperconjugation. This is donating electron density through resonance through a lone pair, all right? All right, so let's do a practice problem. It says, draw the two major products obtained when toluene undergoes monobromination, okay? So the first thing we should do is we should draw toluene. And you guys know that toluene is just a benzene with a CH3 on it, okay? Now this is gonna undergo monobromination, so you got Br2, right, for bromination. And you guys know at this point from the last video that Br2 is not gonna cut it, right? It's just, we need a Lewis acid to get this to go. I'm gonna pick aluminum tribromide. You guys know the other Lewis acids you could use is FeBr3, right? It doesn't really matter which one you use. You just need a Lewis acid. Now, remember what we said, that the CH3 group on the toluene directs at the ortho and para positions, right? So if I just change the color here, you guys know that this is the ortho positions, this is the meta position, and this is the para position, right? And we just said that CH3, a methyl group, like any other alkyl group, is donating electrons to the ring via hyperconjugation, right? Which means what? That means that if it's donating electron density to the ring, it's directing the groups, whatever groups you want to add to the ring, at the ortho and para positions exclusively, right? So what does that mean? That means if we draw our products now, we should get a product at the ortho position, right? This is an ortho position. Doesn't matter which position we pick. It doesn't matter because they're the same, right? Whether I pick one or the other, you guys can see. It doesn't matter if I do this or I pick the other ortho position. Right? These are basically the same, right? These are the same. So I'm just gonna erase one because you guys know that that's the same. But we also need one at the para position. Okay? Now, the question is, which one is the major product? Is it going to be the ortho or the para product? And to be honest with you, this has always been a little bit of a debate. What I'm going to tell you is that majority of the case, the para product is the major product. Para is major. in most cases. Now, the textbook will tell you that the ortho product in this case is the major. So in this case, ortho is major. Now, you're probably wondering why. What determines that? So there's a couple of reasons, and I really need you to pay attention to this because this is super important, right? As far as like, you know, how do we know which one we're going to get? The CH3 is a little bit bulky. I know that CH3 is usually like small relative to like tert-butyl, right? Like tert-butyl groups are like really bulky, right? But CH3 is not that bulky. So it's a little bulky in the context of rings, but it's not that bulky. And CH3 is like obviously the least bulky alkyl group that you can have. So in this case, the ortho product is the major product because from a steric standpoint, it's not that hard to access the ortho position for substitution. So the ortho product is the major product here because sterically, CH3 is not that big, and you can access the ortho position for substitution here. Now, realize that if this was a bigger group, if this was like a tert-butyl group, the ortho product wouldn't be the major product. It would be the para, right? Because you can imagine I had, instead of a CH3 on the benzene, it was a tert-butyl group, right? The tert-butyl group is still donating electron density to the ring through hyperconjugation, just like a methyl would be. But the ortho position is just a little more crowded than the para. And therefore, in that case, the para would be the major product. Okay? If we had to substitute this thing, if you had to add a BR to that thing, it would be para, right? And statistically speaking, I know there's 2 more ortho positions, right, than there is a para position. So you would think statistically you should have the ortho position win over the para. And in this case, it does. In this case, the ortho is the major product. But in pretty much every other case, if you have a bigger group than CH3, the para is the major product in most other cases. Okay, so just pay attention to that because we're going to do more examples related to this. Okay? All right, let's just do another practice problem. It says when ethoxybenzene is treated with a mixture of nitric acid and sulfuric acid, 2 products are obtained, each of which have a molecular formula, C8H9NO3. Draw the structure of each product and propose a mechanism. So we're not going to do the mechanism because we did a mechanism of nitration on the previous video. So we're just going to do A. So what is ethoxybenzene in the first place? You guys should be able to like derive these. I'm just going to draw a benzene, and ethoxy, just like methoxy, means an oxygen on the ring. But instead of methoxy being methyl, it's ethoxy. So we're going to have an ethyl group. Okay? So that's what ethoxybenzene is. And then you're going to expose this with nitric acid and sulfuric acid. So what are the 2 products? Well, we just said that any group like oxygen that's coming off the ring has lone pairs, and one of the lone pairs is going to donate electron density to the ring. And anything that can donate electron density to the ring like this is going to be ortho-para directing, which means the nitro group is going to end up at the ortho position, right? And the para position. Okay? It's really important to remember what your positions are, right? Ortho is closest to the substituent. Meta is one away, and then para is on the very bottom, just one position. There's only one para position, right? Now, which one's the major product? Remember what I said, in most cases, the para position is the major product, right? The only time that we'll see the ortho position be the major product is when you have a CH3 on the ring. But this is obviously a much bulkier group than a methyl group, right? Ethoxy is bigger than methyl. And that's big enough to say, hey, the ortho positions are a little crowded, a little too crowded for substitution, so we would prefer para. So the para position is major. This one's going to be the minor. And we know the real minor, the real minor product is the meta position, but we're not even going to draw that because we barely make any meta product from this. Okay? So that was just a couple of problems to illustrate that concept. Now, let's talk about deactivating groups. So we talked about activating groups, right? There are also groups that deactivate the ring. And how do we classify whether we have activating or a deactivating group? So a nitro group is an example, a nitro group, NO2, is an example of a deactivating group. Why? Well, because it's withdrawing electron density from the ring. So it's removing electron density, pulling it more towards the nitro group. And why is that happening? That's happening because the nitrogen is super electronegative and it's positively charged. Right? So you know that any electronegative atom that's positively charged is dying to get electrons. And it's going to get electrons from the only place it can get it, which is the ring. I mean, yes, you can argue it can get it from the oxygen, but it's looking more towards getting it from the ring, right? So it's having this inductive effect where the nitro group is just inductively pulling electrons away from the ring. And if you draw the resonance of having those electrons go away from the ring and towards the nitro group, you guys can see that now you're generating a positive charge inside of your ring. And like we said, we want the rings to be activating, meaning we want them to be nucleophilic, right? We don't want them to be positively charged. We only want that to happen after it behaved as a nucleophile, right? This is before the ring even touched anything, right? The ring didn't touch an electrophile. The ring didn't even have a chance to be a nucleophile yet. And it's having a really hard time doing that because if these electrons are delocalized on the nitro group, this positive charge is not helping the ring be a nucleophile, right? So this ring is losing electrons to be nucleophilic because the nitro group is just pulling the electrons away. And now we're realizing that when we delocalize these electrons, we're just constantly having a situation where we have a positive around the ring, okay? So this is definitely deactivating the ring. And because of this, we need to really cook this thing up, add a lot of heat to have a nitro group added to a nitrobenzene, right? Imagine we have an NO2 and we want to add another NO2, right? Do another electrophilic aromatic substitution and get an NO2 group on this thing. Because the first NO2 group is deactivating the ring by pulling electrons away from it, you have to cook this thing to 100 degrees to get some sort of substitution, right? And the question is, are we getting ortho, meta, or para in this case? What's going on? Well, if you look at the product distribution in this case, notice we're getting a lot more meta and barely any ortho para. So the meta product is the major product for a group that's deactivating the ring, which is generally a rule of thumb. Now, why is that happening? For deactivating groups, the meta product is the major product. Why? Why is that happening? Because even though this reaction is 10,000 times slower than benzene, you can cook this thing up and get it to go faster, but the meta product is predominant here. And the reason for that is just by looking at the sigma complex for every attack, just like we did with the toluene example. So let's take a closer look. In this case, if you're adding the nitro group ortho, what's happening is, just like we saw before, how the positive charge ends up adjacent to the substituent, this group, right? Before this was a CH3, now it's NO2, which is deactivating. Now, if I asked you, is this a good situation? Because now you got a positive charge adjacent to an electron withdrawing group, not a donating group, a withdrawing group. Guys, if you have a positive charge next to a group that's trying to pull electrons away from the ring, that's not a good situation, because this positive charge is not stable. It would be stable if this group was a methyl group or a methoxy group, because then you can have electrons feed the positive, right, and stabilize the positive. But this group is not feeding the positive. If anything, it's making the positive worse by withdrawing electrons away from the ring. Right? We're not feeding that positive, we're just making it worse. So that's why this does not want to attack ortho, because you have a positive charge that's just not stabilized. Even though you can move the positive around through resonance, yeah, sure, but it's not a favorable situation. This sigma complex is less stable. Right, now, if you look at the meta position, if you do the attack at the meta position, then the positive charge is nowhere near what electron withdrawing group. It's not, right? Like, you can delocalize this positive charge, and nowhere is this positive charge next to or adjacent to the electron withdrawing group. So in many ways, the meta attack is allowing to have a little more stable of a sigma complex relative to your ortho attack, right? The meta attack is a little better. It's not great, but it's better than the ortho. And you can cook this reaction up and it'll work at the meta position for this reason. If you look at the para position, you end up with a similar situation. If you have an attack at the para position, notice if you delocalize the positive charge around the ring, the positive charge ends up making its way next to the withdrawing group. Similar situation to the ortho. We do not like that in this case. All right, so this is not a good situation where ortho para have a positive charge delocalized right adjacent to an electron withdrawing group. Not good. But with a meta, you don't have that. So this is explaining why the meta product is the major product for a deactivating NO2 group on an aromatic ring. Right, and I kind of make that point here. Electron withdrawing group deactivates sigma complex from orthopara and therefore is a meta director. So general rule of thumb is that any sort of deactivating group is going to direct meta, not orthopara. Right? Activating groups are orthopara, deactivating groups are meta directing. Okay? And I highlight that on the slide. All electron donating groups, activators, orthopara directing. All electron withdrawing groups, like NO2, which is a deactivator, is a meta director. Okay? Except the halogens. So halogens are an exception. And we're going to talk about how halogens are a little different. They're a little special. And why are they a little special? Well, halogens can withdraw electrons by induction, right? If I have, for example, chlorobenzene, okay? Chlorobenzene, chloro is a halogen, you guys know that, and it's withdrawing electron density because it's pretty electronegative, right? So it's going to withdraw electron density from the ring. But at the same time, it can actually donate electrons to the ring through resonance. And why can it donate electrons through resonance? Because it's got a lone pair right next to the double bond, right? And you guys know through resonance, if I have a lone pair that's adjacent or next to a double bond, I can donate electrons to the ring through resonance. And you guys see how the ortho and para positions have negative charges, and they're basically activating the ring. So what the hell's going on? They're actually not activating the ring. They're deactivators, technically, because they can withdraw electron density from the ring. But they're ortho-para directing because they can donate electrons through resonance. So yes, resonance typically is a dominating factor, but in this case, it's an exception. The induction is the dominant factor for halogens, and that's why it's deactivating the ring. But it's still ortho-para-directing because of resonance. And to illustrate that again, just like I did before, you guys can see that if we do an ortho attack, looking at the sigma complex and the resonance structures, you have an additional resonance structure where the positive charge is delocalized on a chlorine, which is nice because if you have a positive charge delocalized over a larger atom like chlorine relative to carbon, that's a better situation, right? Any charge that's delocalized on a larger atom is usually better, right? So that's just providing an additional stability to this complex, right? Versus if you look at the meta attack, you don't have that happen. The positive charge is not delocalized anywhere so that it can be on the chlorine, and it's not next to or adjacent to chlorine, which has a lone pair that can donate electrons, to stabilize this positive. So, you look at the para situation, it's a similar situation where if you attack para, the positive charge can get delocalized on the chlorine. And given that you have an additional stability here, halogens are ortho-para-directing even though they're deactivating the ring through induction. That's just one of those exceptions. Honestly, if I were you, I would just be like, hey, if I have a lone pair that's adjacent to a positive, I'm ortho-para-directing. Like, that's it. That's really all you need to do. You're like, okay, do we have a lone pair next to, adjacent to a positive? If that's the case, then you pretty much know you have an ortho-para-directing group, okay? Even though technically halogens are dubbed deactivators. So with that, let's look at some activating groups. So we saw how CH3 is activating, methoxy is activating, right? These are all ortho-para-directors. Here's just some more examples, right? Notice the trend here is that if you have a lone pair that's immediately adjacent to the aromatic ring, you can have that lone pair feeding into the ring, right, through resonance, and it's, becoming more electron rich, which is why, and it's becoming electron rich at the ortho and para positions, as we saw earlier. So really any sort of group that has a lone pair adjacent to the aromatic ring is going to be a strong activator, okay? Here's an amine, right? A primary amine, secondary amine. These are all strong activators because of that lone pair. But we also have moderate activators. Now, moderate activators are also ortho-para-directing. And why? Because they have that lone pair that can donate electrons to the ring, right? Except the lone pair can also donate electrons outside of the ring, right? And if the lone pair can donate electrons outside the ring, it kind of diminishes the ability of the same lone pair to donate electrons into the ring, right? So this same lone pair, it wants to go this way into the ring, but because it can also go outside of the ring, right, the other way, it's diminishing the effect of that donating capability. So that's why it's a moderate activator, right? It's not as strong as when you have a lone pair that can only go into the ring, right? So this is a little bit weird though. Let me go back to the pointer. Technically a methoxy or alkoxy group, kind of like methoxy, it should be a strong activator, right? Because the R group doesn't really have anywhere that this lone pair can go, right? You would think this lone pair can only go into the ring, right? Not outside the ring. But for whatever reason, it's dubbed a moderate activator. And I actually kind of disagree with this. This is in the text. I would still think that this is a strong activator. But in the textbook, they call it a moderate activator. So that's just the reality of it. Like I said, I don't entirely agree with that, but that's just what they say. And there wasn't really any good reason for it, and um, we don't have to worry about that so much. Just know that this is a moderate activator. Now, alkyl groups are weak activators because one, they don't have any lone pairs to donate to the ring, right? And they only donate to the ring via hyperconjugation, right? So that's a pretty weak effect relative to a lone pair. Okay, so any alkyl groups are weak activators. All right, what about strong to moderate deactivators? So we just saw that a really strong deactivator is a nitro group. Here's another deactivating group, right? Like a positively charged nitrogen. You rarely see this, but if you do, just know it's deactivating. Why is it deactivating? Because we just said nitrogen that's positively charged is dying to get electrons, right? It's electronegative and it's positive. That's not good, right? So it naturally is going to want to pull electrons from the ring and deactivate it, right? Here's another example where you have 3 halogens on a carbon. Now, we said carbon groups should be donating, but because of the withdrawing inductive effects of the halogens pulling electrons from the carbon, it's actually more of a deactivator here. So all of these groups are meta-directing, pretty strong deactivators. Moderate deactivators are basically groups that have a pi bond to an electronegative atom, right? And the pi bond is conjugated with the ring. Here's an example, right? So notice that there's a pi bond that's next to the double bond. And how can this happen? You can show, here, let me put my pen here. You could show a resonance structure where, you know, these electrons are being pulled from the ring towards that pi bond with an electronegative atom, right? You could do the same thing over here with the aldehyde, right? That's a ketone. You could do that with the ester. You could do that with the carboxylic acid, amide, right? All of these groups can do that. But really the key thing here is you'll notice that there's no lone pair next to the ring to donate electrons, right? That's another clue as to why this is a deactivating group. Okay? Moderate deactivator though. Not too strong, but moderate. And then we just talked about how the halogens are technically deactivators, but they're weak deactivators because there's this delicate competition between resonance and induction. I do highlight over here, I say, you know, halides are the only deactivating groups that are ortho-para directors. Okay? Here's a nice table that kind of summarizes all of the groups and how strong, moderate, weak, you know, the groups are, whether they're activating or deactivating. You should be able to recognize these. I'm not saying you should memorize this table in any way. Just know when you see a group, you should be able to classify it as a strong, moderate, weak activator or deactivator. And we'll practice some questions related to that. Okay? For example, if you look at this problem, it says, consider the following monosubstituted aromatic ring. Predict whether this aromatic ring is activated or deactivated, and predict the strength of activation / deactivation. You know, i.e., is it strong, moderate, or weak? And then predict the directing effect of the group. Okay, so let me go back to the pen here. The first thing you should look for is there a lone pair that is directly adjacent to this aromatic ring? Is there a lone pair on that nitrogen? Yes, there is. There's a lone pair. If there's a lone pair, what does that mean? That means it can donate electrons through resonance to the ring, which means if it's donating electrons, right, through that lone pair, it's an activator, right? It's activating the ring by putting electrons in it. It's an activator. But is it a strong activator? Is it a moderate activator? Or is it a weak activator? We know it's not weak because the only weak activators we saw were the alkyl groups, right? The ones that didn't have a lone pair. But this lone pair can also be delocalized outside of the ring, right? Which means it's not a strong activator because that same lone pair can be pulled away from the ring and not donating to the ring. So it's not a strong activator, but it's a moderate activator. And if you don't believe me, we just looked at examples of moderate activators, right? Moderate activators exhibit a lone pair that is already delocalized outside of the ring, right? Which diminishes the capability of the same lone pair to donate into the ring. All right. Here's some practice problems that you can try with this, right? Why don't you try these on your own? I'll post the answer key for this as well. But you know, in general, you should try to give these a shot. I'm not going to do these for you. I want you to try. Okay, that concludes this segment. So there's going to be a third video talking more about how we can substitute the ring with multiple substituents on a ring. So stay tuned for that. I'll see you in the next video.